Hello everyone, so welcome to the final lecture for week 10. So we will discuss about some other aspects of parameter efficient methods. So we have talked about LoRa and QLoRa in detail. So in this lecture we will talk about pruning and distillation edge and some other aspects of parameter efficient methods. So these are the concepts we will cover. We will talk about pruning briefly and also the distillation aspect. And these two are used again for parameter efficient fine tuning methods. So they both bringing the parameter aspect again. So we talked about one way where you can approximate the delta W parameters, the change in the so you have W naught plus delta W. So you can approximate this change through a small set of parameters, right? So through a small set of parameters. But now what we will do, we will say, okay, why can't we do something with the parameters? Why can't I reduce the entire parameters altogether? So this will also bring in efficiency at the inference time, because right now this helps in the fine tuning time, but inference time you still have to use the same original big matrix. So can we do something so that we can reduce the number of parameters altogether of the model? So both these techniques, pruning and distillation, help in that. Okay. So let's talk about them these one by one. So let's say what is the difference between pruning and distillation. So in and the quantization, right? So we talked about quantization. So in quantization, you don't change the parameters. You only store them in low precision, the 4-bit or 8-bit precision. So up to some k bit of precision. You don't change the parameters, right? You just quantize them, dequantize these for operations. In pruning, you will actually change the parameters. That means you will put certain parameters to 0, and that's what you mean by pruning. So these parameters you specify are not needed for your computation. I will not use them in my computation path. So your number of operations decrease to a large extent, and the remaining parameters are not changed, right? So you either use a parameter or you don't use a parameter. So you have a binary mask with each parameter, whether I'll use it or not use it, right? So yes, in some way it looks like dropout, but in dropout you randomly decide. I mean you have a random, you have a probability for each parameter whether you want to include or not include. Here you deterministically say that okay, at inference time I will not use this parameter at all, right? So that's what is pruning. So why do people think that pruning works? I mean, the main idea is this lottery ticket hypothesis, which says that okay, if you have a pruned randomly initialized network and you train that, that will be better than training the full randomly initialized network, right? So idea is that yes, there is a pruned network with a smaller size that will do nearly as well or even better than what you are getting from this large model. Yeah, but yeah, I mean it doesn't specify how do you find that particular pruned network, but this at least gives this is just hope that yeah, you can find a pruned network where you can have a small number of parameters, but you can still get similar sort of accuracy. Yeah. So what are the different ways you can do pruning? So there are various methods of pruning, but the most simplistic is the magnitude pruning. So what is the idea? So let's say you have already trained your model, you have your parameters, and now you can find out the weights of the parameters, right? So you can say which parameters have the smallest weight. So you can take the x% of the parameters with the least magnitude and prune them. That means put them to 0. So it's not like a structured pruning, because you are saying any parameter which has a weight below a threshold that is determined by this x% of parameters, you will remove that. And like this, people have seen that if you prune the parameters, if number of percentage you are pruning, you see at least at some point it gives you the same performance, yeah, as the original model. So even if you prune at certain point, it will give you roughly the same performance. Okay. So this was the magnitude pruning. You can also do movement pruning. What is movement pruning? So you already have some, let's say, pre-trained weights. So you have a pre-trained weights, and then you fine tune those parameters. So let's say these are your fine tune weights. Now in magnitude pruning, what you will do after you fine tune these, you will see which parameters have a value, I mean below a threshold, right. So you will say minus 0.5 to 0.5, you have any parameter that comes in range, this gray zone, I will remove it, right. So I will not use that because the magnitude after fine tuning is very, very small. The movement pruning idea is that, okay, they already had some weights in the pre-training. When I did fine tuning for a task, how much these parameters move from the pre-trained weights. So some parameters would move away from 0 and some parameters will move towards 0. So the gray ones are those for which the pre-trained weight was higher than the fine-tuned weight, right. So pre-trained magnitude was higher than the fine-tuned magnitude. That means the importance of this weight has gone down after for fine-tuning for this task, right, both sides. So idea is that, okay, that means this parameter may not be so important. On the other hand, some parameters, even though their magnitude is small, they have gone away from 0. That means their magnitude for the fine-tuned task has increased compared to the pre-trained task. So they may be important for the fine-tuned task. So I retain these, but anyway, any parameter that has gone towards 0 and magnitude has reduced, I will prune this. That is the movement pruning idea. There are other things, for example, what if I see how much, see the large input can impact a certain weights, right. So this is Wanda method. So what they saw, let's say I do magnitude pruning. So these are my weights, right? These are my weights, and what I will do, let's say I try to find some threshold, below a threshold, if the magnitude is there, absolute value, I will remove it. So this is after doing absolute value, and then I say, okay, these weights have a small magnitude, I will remove them. What will happen? All these weights, right, in this particular dimension have been removed. Now suppose you get a input like this, so 1, 2, 8, 3, so which has a very large activation in this dimension. Now you will multiply it with 0, right, it will not have any impact. So what Wanda said, that compared with the magnitude pruning, so given a weight matrix and input feature activation, they will compute the weight importance as the element wise product between the weight magnitude and the norm of input activation. So you will not first prune. So you will first see, given my data, what is the impact, I mean, so what is the weight times the data, right. So that means, so you have 401 minus 1, take absolute value, multiply by the actual data. So you will get 4083, right. In this, I can now prune. Let's say I have to prune 50%. I can say, okay, I'll prune this and this, right, because they have the smallest w time dot x value. Similarly, for this particular dimension, you say, okay, so if I multiply 3, 4, 8, 9, so these two have the smallest value. Similarly, if I multiply, I will get 3, 2, 0, 6. These two have the smallest value. So this becomes my pruned weight, right. So it is dependent on my data. So maybe data is such that it has a high value, high activation in certain dimension. So you don't want to prune a priori without looking at your data. So you want to look at your data and see, okay, the data multiplied with the weights, where do I feel importance, where do I feel this is not important, right. So that's Wanda method. So you prune by weight and activation together. Yeah. So rather than globally across the entire matrix, you use w dot x2, right. Okay. All these are unstructured. They don't say, okay, if your network has a structure, like we talked about a multi-head attention, feed-forward layer. So you're not removing like certain heads, or you're not removing certain feed-forward layers altogether. You're just saying, okay, I'll remove the weights that satisfy certain property, right, or that do not satisfy certain minimum criteria. So there is also structured pruning. So where we say, okay, I will structurally, I mean, remove certain parts of the network rather than saying, okay, any neuron can be removed or any attention thing can be removed, right. So they will have two components. One is the self attention. So typically transformers have self attention and feed forward network. Idea will be, so for each such network you learn a mask, that whether I want to retain this or I want to remove this. Okay. So I can turn off certain components whenever I need to turn off, right. So I learn which components I can turn off, right, and others are retained as it is, right. So certain components as a bulk are removed. So you can have some very coarse mask that, okay, in this particular layer, layer 5, I will remove the self attention block altogether, or layer 6, I will remove the feed forward block altogether. Or you can have fine mask that, okay, in this particular layer, in the self attention, I will zero out certain attention heads, right, or in the feed forward thing, certain dimensions I will remove. So you can have some coarse mask or fine mask at feed forward layer, at multi head attention, even at the embedding layer, right. You can remove certain parts or the entire block. So you see, you have the entire block can be removed in a layer, or you can remove certain dimensions of that, certain heads of multi head attention, and so on. Like this head can be removed in this multiple heads. Certain dimensions of the hidden layer can be removed. So and that is your structured pruning. So so what you will do, you will have some mask like here. So you have a mask that is 1 or 0. So if it is 1, you are retaining that head. If it is 0, you are getting rid of that head. Okay. You can have a mask for the entire multi head attention block. That is, okay, if it is 0, that means I will not take this multi head attention at all. Same with feed forward layer, you may have a mask. So they have only value 0 or 1. So if it is 0, I will not take that feed forward layer. Or you can do it over just the certain hidden states of that. So you can have a separate diagonal matrix. So these values can be put 1 or 0. So if they are 0, you are removing certain dimensions. If it is 0, certain dimensions from WD are not considered, right. So you can do it at coarse level. So both this and this are coarse level, and this are fine grained level, right. And you have a mix of this. So you learn which of these have to be put to 0 through your data, right. Like this example, you are removing certain parts of your embedding, you are removing these two heads. This is fine level. You are also removing this dimension from the hidden layer in the feed forward network. Here you have a coarse level. You are removing this entire, both the multi head attention as well as feed forward from this layer 2, right. So initially you started with 6 as the input dimension, ds was 6, and now you pruned 3. So you get ds 3, right. You had 3 feed forward layers here, and now you have only 2, and similarly you had 4 heads, and now you have only 2, and same with this hidden dimension, you have 8 here and you go to 4. So you can do structured pruning, right. So that's the idea. So now after pruning, next we can talk about distillation. So what we do in distillation, right. So distillation is a very commonly used idea, that suppose you have a very large model. So we call that a teacher model. So you have a teacher model, that's a very large model. You want to train a very small model. So what you will do, you will say, I will distill this model and train a student model. An idea is that the teacher student idea, that means the student model will try to replicate the behavior of the teacher model, right. So in distillation we try that the student model is trained by mimicking the behavior of the teacher model. Okay. Now let us try to compare it with quantization and pruning. So we talked about quantization, no parameters are changed up to some k bits of precision. Pruning, some parameters are removed altogether, some parameters are retained as it is. Distillation, you change everything, right. You have a new model altogether. You change all the parameters, you learn new parameters. This will be again a subset of the original, I mean the size will be much smaller than the original size of the model, but you change all the parameters. So what is the basic idea? How do you do this? And the idea is the normal weak supervision idea. So, so idea is that you take a lot of data, you have a teacher model, and using teacher model on some unlabeled data, you generate targets. So what will be the target generated by the teacher model? So let's say you are doing a classification task, you take a lot of data and use a teacher model that is assumed to be like well trained to generate labels. These are called pseudo labels because they are not ground truth, but they are coming from teacher model, right? And now from these pseudo labels, you train some student model, right? So you start assuming that pseudo labels are the actual labels, and you train on the pseudo labels, right? So and that many different ideas adapt this particular concept. Now, what exactly is done in distillation? So there are two ways you can do distillation. One is using hard targets. Second is using soft targets. So now we talked about unlabeled data. So let's say you have some unlabeled data. Now you can apply teacher model on this. Now you can either generate the labels, and this is what called the hard targets. And let's the student will try to mimic these hard targets, right? So I say, okay, I give a sentence, my teacher model will give me the particular sentiment, say positive. Now the student model should be trained such that it gives me the same sentiment class. So that is called hard target. But then you can even go more fine-grained level, saying, let me generate the soft targets. That means just the distribution. So suppose teacher model gives positive 0.9, neutral 0.08, and negative 0.01. So I'll now try to train a student model such that its label distribution matches that of the teacher, right? And this is what is known as the soft target based distillation. And what has been seen, so soft targets are typically better than hard targets. So they get a better accuracy at test time rather than just asking them to predict the final label. It's better if you give the entire distribution, let them match the distribution, then they mimic the teacher much better. Okay. So that's the difference between hard and soft targets, and soft targets are typically more popular to used in the case of distillation methods. Now, when you talk about language model, distilling language models, so you can say, can you have soft targets for the whole sequence, right? So first of all, we can have the word level distillation. That means, see, when you predict the next word, you will have a probability distribution. So I am having to predict the next word from here. So the teacher model will give me a distribution over the entire vocabulary. And the student can match the distribution, right? So idea will be simply this divergence kind of loss. So you have the probability of the student model and the probability given by the teacher model, and you try to minimize this loss, the divergence between this, right? Minus probability given by the teacher model times log probability of the student model, right? So that is one loss, the word level distillation loss. So you're trying to match the distribution. If they are not matching, you give an error, and that is used to backpropagate, right? The second thing is sequence level distillation. What is the idea? So you, in a certain generation scenario, you let the teacher model first generate the sequence. So teacher model will first generate the sequence, and then you will try to maximize the probability of that sequence by the student model. So you will compute the probability of that sequence by the student model, and you try to maximize this, right? That's like giving it a gold standard that, okay, you do your next token prediction through this ground truth, that is a sequence generated by the language model. So in effect, it tries to learn all the sequences that are generated by the teacher model. So student model learns to mimic the sequences generation from the teacher model, right? And then you can mix these two losses. This is at the word level distribution, this is at the sequence level probability by the student model. This you are maximizing. So So minus log probability. Okay. So one of the very particular model that has been trained through this idea is the Distilbert model. So this came from BERT. So you started from BERT, and what you do, BERT, let's say, has 12 layers. So they took only half of the layers. Right? So they took half of the layers and 60% of the total parameters. So how did they take half of the layers? They will just take alternative layers from BERT, right? So that you have information from across the entire span of BERT, and then you use supervised loss and also distillation based loss, right? And that's what they found. The distillation based loss was the ones that helped primarily in this training process. And one more thing that they tried to add is that the hidden vectors that you are getting in this Distilbert should be very close to the embedding of the teacher, right? So the teacher and student, the hidden vector should be very close. So this is another loss they were adding, that finally the representation you are learning should be very similar to the teacher model. You should not diverge too much from that. So okay, with that you went from say 110 million parameters in BERT to 66 million parameters in Distilbert, and even and you see the inference time also becomes smaller, and performance wise there were some versions and it slightly degrades, but I mean reasonable performance with low parameters. This is at the inference time. Inference time you just have very small number of parameters compared to BERT model. Okay. Now there is also a recent paper which says this idea that once you generate the sequence by teacher model and let the student model mimic that generation doesn't help in the generative models. So what is the problem with this approach? The problem is that you are generating a sequence through teacher model and asking student model to have a high probability for that. So it will start mimicking. So it will start memorizing the samples generated by the teacher model, but it does not learn what not to generate, right? So maybe some sequences that have very low probability by the teacher model, it has never seen that in that process, and it may overestimate the probabilities for those, because it has been trained only for the sequences to maximize the probability of certain sequences. So it will start overestimating even the low probability regions of the teacher distribution. So how to avoid this? They just reversed this idea. They said, okay, let the student model generate a sequence first, right? So student model generates a sequence, and the teacher gives a feedback that is this a good probability sequence or it's a bad sequence, and teacher gives a feedback. And this feedback can be as simple as just finding the probability. Okay, how much probability would I have given? I would have given it a very low probability, right? So you don't generate such a sequence, right? It can be as simple as that. This is the reverse process, right? So there, what we were saying we will take a sequence generated by the teacher and let the student maximize the probability for this. Here, opposite, let the student generate a sequence and the teacher gives a feedback, is that a good probability sequence or not? That's why they call it the reverse KL divergence formulation. Okay, right. So yeah, I mean this ends our week 10. Of course, there are many more aspects about parameter efficient methods. We had covered some that will be very important for you to train and build your models. So in the next week, we will come up with more details on various large language models, scaling laws, various architectures, and we will see how to handle long context even better than what we have seen in the week 5. Thank you then.